Oh, there it is. Cool. Yeah. Oh, wow. Geez. Oh,
Water, the essence of life.
Okay, Janine. So we need to make a documentary about water for CUAHSI.
Yes, it's a Let's Talk About Water documentary, and right now we have a lot to do, so we have to brainstorm. What do we need to do? We need to find experts who know about the stuff,
We need to get footage about water.
and we need to figure out the name of the documentary and the topic.
Okay, so now that we have the title and the three topics, fire, flood, and snow, what should we do?
Yeah, it's good. We're making progress. I think the next step is we need to figure out which topic we're going to document first. So which one are we going to do? Let's think about this.
Should we get some coffee?
Yeah, that's a good idea.
Hey, man.
Oh, hey, drink that.
Hi.
Hey.
So what about doing Snowstorm for the movie?
Yeah, that's a good idea.
Movie? What movie?
Oh, we're filming this documentary on the manifestation of water and natural disasters, and so we're looking at flood risk and coastal erosion, snowstorms, and wildfires.
I work on wildfires.
Oh,
Yeah, you can use some of my work for your documentary if you're up to it. That would be great.
yeah.
Thanks.
Wildfires. They impact the ecosystem and modify fuels and redistribute carbon, water, and energy between ecosystems and the atmosphere.
I love the idea of having different phases of water represented in our research. The conditions for wildfires are right when evapotranspiration occurs and, water from the plants and from water bodies are evaporated due to, increasing atmospheric heat, for example, drying out the fuels, drying out the vegetation.
These impacts highlight the concern about changes in fire activity.
Wow, this is pretty intense.
Yeah, so you could see, like with Tirsa's stuff, you can see how the wind does move around. This is a very open, there's no mid-story here, so the wind is gonna intuitively move around.
It's therefore important to gain a quantitative understanding of the drivers influencing changes in fire activity for improving modeling and prediction studies in guiding adaptation strategies.
My work is on fire-induced turbulence within the forest canopy. So typically you see patterns within certain physical quantities, such as temperature, arising out of wind-induced turbulence both within the forest canopy and outside the forest canopy. When a cool parcel of air, which contains carbon dioxide and water in its gaseous form, which is basically water vapor, gets swept into a canopy because of a downdraft, it starts to collect heat from the forest surface. Its temperature starts to increase as a consequence of that. And if you were to plot the temperature versus time, you would see that the temperature increases along a ramp. When this air parcel gets ejected out of the canopy, the temperature drops suddenly along a cliff, and this is what we call a ramp cliff-like pattern. And we're trying to see how these patterns get modulated by the presence of a fire. What we expect to see is that the cool air parcel would get heated much more rapidly because the fire is a very strong source of heat, so that the temperature would rise to a very large value in a very short duration of time. I'm trying to ask and answer the question, can we corroborate this by looking at some experimental forest fire data?
And that's exactly what wildfire researchers are working on.
I work on the wildfire research using multiple geographic analysis tools to look at fire distribution temporally and spatially, and also using the drone to look at the wildfire behavior and also their impacts to the environment before and after the fire. Drone is a really useful tool to monitor the environmental to monitor every environmental phenomena. Because it's small and it can fly across the forest, it can fly above everything that we want to monitor, and we can attach several types of the sensor to the drone. For example, now this drone is attached with a LiDAR sensor, and it can scan the vegetation and the forest in a 360-degree, so that we can collect all the detailed information we need. And also we have some sensors like the thermal sensor and the multispectral sensor. With these sensors, we can monitor how the fire evolved by looking at the fire front line during the fire, and also looking at the variation in the vegetation structures before and after the fire. Especially using the multispectral sensor, we can look at the healthiness of the vegetation. All these impactors, all the factors like the water, the gas, the atmosphere, they have a very complicated connection. And so using the drone and their different sensors, we can get the information about the fire and also the forest ecology from every perspective we need.
And one of those perspectives includes ground observations.
My name is Margarita Rivera. I'm a PhD student working on wildfire research, and I'm going to talk to you guys about a sonic anemometer and how we use it for wildfire research. Another of the projects that I'm involved in and working on is during prescribed fires, we also take measurements before, during, and after the fire. One of the instruments that we use, it's this sonic anemometer right here. This is a 3D sonic anemometer. It's used to measure average horizontal wind speeds and direction and the turbulent fluctuations of horizontal and vertical wind. And then with these measurements, we can get the vertical profile of the wind during a prescribed fire. And this helps to better understand the erratic behavior of fires. This is an example of the new kind of anemometers you can get, which are way more compact and just easy to travel and work with.
Yeah. There you go. Now you can bring in your
From wildfires to prescribed burns. For many, fires are an essential part of life, and water plays an important role in its existence.
Instead of water, we use dirt.
No, you just do all of them. You guys have to do one.
Alright, so now we know we're gonna stay for wildfire.
Yes. Check.
Nice.
Okay, Alex, so we did wildfires already, so what should our next topic be?
Let's think about snow.
Yeah, that's a good idea.
Oh,
Flood
risk warning.
In Southern California, we have something called the fire flood cycle. Droughts lead to those dry conditions. Wildfires happen. They remove the vegetation from the hill slopes, right? And that makes the soil less stable because the vegetation roots are not holding the soil anymore. Also, if the fire is pretty severe, it can combust the organic matter, and the soil just becomes a lot less stable.
The tractor sick too. Wow. So at any point, one of those layers could just be just peeling off. Yeah. Just slide off on us.
Next part of the cycle, in the winter, the storms happen, and they can wash a lot of that soil into our streams. And the way that flood risk happens is in Southern California, we have this type of infrastructure called a debris basin. It's kind of like a big, you can think of it like a bathtub at the foot of the mountains. But the way that wildfire kind of increases flood risk is that there's more sediment from the hill slopes and the stream. So essentially that fills up the debris basin faster, right? And if you have multiple storms in a row, the debris basin can fill all the way up and overflow. That's a problem because the
the mixture of sediment and water enters the flood channel, and it's only designed for water, so it essentially fills up with sediment or can get clogged, leading to downstream flooding. I kind of think of the phases of water involved in that are evapotranspiration, right, when the fuels are drying, the vegetation is drying, but also liquid, because you have these series of storms that are pouring down lots of rain onto the land surface, and that turns into runoff, which can cause floods.
And another way water manifests itself in natural disasters is through coastal flooding.
I'm interested in coastal erosion and its implications for flood risks. Beaches also serve a really important function. They are nature's defense against coastal flooding. So they almost act as a buffer between important infrastructure or wetland habitat from damaging coastal waves and forces. So you can imagine with a wider beach and maybe higher dunes, we have more protection from coastal flooding. I think it's important when we understand beaches is to understand, where does the sand actually come from? Many beaches are formed at the end of a very large watershed. That means all that sand is coming from land. So over time we have, rock eroding away, becoming sand and sediment. Then we'll have a big rain event come in, flush all of that sand right to our coast, and then that is where beaches grow. But the sand doesn't really just stay in one position on the coast. It's actually in constant movement. You can almost think of it as like a river along our coastline, where we have sand moving up and down the coast, onshore and offshore, being forced by waves, currents, and winds. Unfortunately, our beach systems are under threat. We have disrupted sediment supplies when we build dams and we channelize our river. This reduces the amount of sediment that naturally would come to our coast. We also have rising sea levels and uncertain future wave conditions, which means that there's a lot of uncertainty when we try to approach strategies to defend our beaches, but also defend our infrastructure. One of the main tools we can use as coastal engineers to understand these coastal processes are drones. Now we can use both LiDAR and also photogrammetry-based methods. So we can actually reconstruct the beach using these drone data sets, so we can understand which part of the beaches are eroding, which parts are maybe accreting, and then we can connect that with different wave forcings that we see at the time, and we can get a better idea of what parts of the coast are changing, why, and maybe what can we do to help stabilize our beaches.
So now we know what we're going to talk about for flood risk and coastal erosion.
Flood. Done.
Nice. So you look at the next one. Yeah. Is you?
Okay, finally we can do the snowstorm. How do we get snow from liquid water?
There is a concept called lake effect snowfall, and that's where water influences snowstorms.
I didn't know. Tell me more.
Okay.
Minus 24 degrees Celsius. We're gonna start our trek.
So water can manifest itself in the form of solid state precipitation when we're talking about snowstorms. And one way that we can see a lot of heavy snowfall is the interaction between the lake and the atmosphere. This is called lake effect snowfall. And you can see this on the radar behind me. It really occurs when there is a really warm water body and cold air advecting over the lakes. And so what happens is there's a transfer of energy from the water into the atmosphere that fuels convective processes, increases the amount of moisture into the atmosphere, and allows for heavy snowfall to fall on the leeward side of the lakes. So these snowstorms can be very localized in nature, and they're very difficult to predict depending on many different variables such as the topography, the lake bathymetry, and having the right atmospheric conditions that are favorable for the development of lake effect snowfall. For lake effect snowfall to occur, you need to have at least a temperature gradient of 13 degrees between the lake surface and the atmosphere. You also need to have winds that are moving along the long axis of the lake. You need the lake to be an open water body. So if there's ice that's over the lake, that inhibits the amount of energy and moisture that can be transferred into the atmosphere.
Therefore, when considering lake effect snowfall, water is manifested in 3 different states: liquid water over the lakes, in its gaseous form through evaporation into the atmosphere, and falling as solid state precipitation.
We're all familiar with water in its solid phase, in the form of ice in our freezers or snowstorms during the winter. Ice and snow impact all our lives in both beneficial but also disastrous ways, perhaps the most dramatic example of which are avalanches. If you've ever lived near a mountain range or gone skiing in one, you know that avalanches can be deadly and destructive. But much like forecasting the weather, scientists in avalanche-prone areas are constantly trying to anticipate the probability of an avalanche occurring to ensure safety of local residents and infrastructure. Scientists draw conclusions about the risks of an avalanche occurring by analyzing data they have access to about the snowpack, mountain topography, and weather conditions, combined with their experience. Forecasters have to deal with uncertainties and unpredictabilities in everything from the accumulation during snowfall, to the contours of the mountains, to the microstructure of the snowflakes themselves and the snowbed. Local weather conditions like temperature and the amount of sun will further change the snowbed, as will the gusty wind on the mountaintops blowing the snow around, a process which is known to strongly affect avalanche occurrence. All these processes have their own forecasting models and their own uncertainties, which have to be incorporated together for accurate avalanche prediction. Those same models we use to forecast avalanches are also crucial for predicting the evolution of mountain snowpacks and glaciers in a changing climate.
And as our climate continues to change, it is imperative to have accurate weather observations.
So my job is to try to use a satellite to measure how much rain and snow falls on the ground. We have this satellite, which is a GPM satellite, Global Precipitation Measurement Mission, that carries actually 2 radars. So it works very well. It gives accurate measurement of precipitation everywhere around the globe. The only drawback of a radar is it is quite a large instrument. It's heavy. It requires a lot of power to operate. So this satellite is about the size of a minivan. It's a relatively expensive satellite. Because it's heavy and big, it's also expensive to put it on a big rocket to send it to space. So one thing that we do with this satellite measurement of rain and snow is verify if the models that we have that reproduce the Earth's climate are accurate. What the models say about what is happening with climate change and will keep happening in the future is that the regions that are dry will tend to become drier, and the regions that are wet will tend to be wetter. So more rain in tropical region and maybe even less rain in semi-arid region like Southern California.
And with anthropogenic climate change, continued advancement in hydrological sciences is needed to understand the complex roles of water in its different states as it manifests in wildfires, flooding events, and snowstorms across North America and the world.
Okay, finally, now we have a plan for Snowstorm.
Nice.
Okay, I got the title, we got the topic. What's next?
We just need to find the experts.
When?
I have no idea.